Okay, this one is hard to explain in words. You have to just see it. So let's go directly into it. We have a solution that contains 0.2 molar of calcium nitrate, cadmium nitrate, and magnesium nitrate. Forget about the nitrates. Those are just counter ions. They're solutions of 0.2 molar magnesium, 0.2 molar calcium, and 0.2 molar cadmium. That's what's sitting in a beaker right now. Then we add solid sodium oxalate. The reason it's solid is so that we don't add in, we don't want to put in more water to change the concentration. So this way we can avoid the mixing. By adding the sodium oxalate in solid form, we don't have to worry about changing to moles or anything like that. We're just going to add in the small amount of sodium oxalate a little bit at a time. See, it doesn't say how much. So since it's oxalate, the oxalate ion is C2O4 2-. So looking at the table, you'll see that we will be creating magnesium oxalate, calcium oxalate, and cadmium oxalate. And this has, for the KSPs for this, magnesium oxalate is, where are you? 8.50 times 10 to the minus 5. Calcium oxalate is 2.30 times 10 to the minus 9. And cadmium oxalate is 1.50 times 10 to the minus 8. And each of these, if we write out the whole, oops, this is magnesium, write out the whole expression that we'll be using. And then this is calcium times the concentration of oxalate ion. And then this is cadmium ion times the concentration of oxalate ion. That's what they're equal to. Those are their expressions. Now the first question is, in what order do these ions fall out? Well, if you we'll do calcium first, and that's how I had it originally on my paper here, so I want to go back to that because I keep messing up. The calcium is going to be, if we rearrange this expression here, we end up with 2.30 times 10 to the minus 9 over 0.2. That gives us 1.15 times 10 to the minus 8 molar. Well, if the concentrations, if we think in terms of QC, the concentrations of the calcium oxalate, if they're greater than this number, then there will be a precipitate. If they're less than that number, then they won't precipitate. And if they're exactly that number, that's just when they start to precipitate. So this is the point. This is the concentration when PPT begins, just as it begins. So you could say it's actually slightly larger than this when the precipitation comes out, but let's just go with that. Right at that point, you add in one more ion of oxalate ion, that's when it's going to fall out. So that's the concentration when the calcium will begin to fall out. For cadmium, we can figure it out as well. The concentration of oxalate ion that has to be added to get the cadmium to fall out is, we just take this KSP divided by its concentration of the cadmium, and when we hit 7.5 times 10 to the minus 8 molar of the oxalate ion, that's when the cadmium begins to fall out. Then we do it for the magnesium. You can see they're all different, and they should be. If we want to take out one of these ions at a time, then they should fall out at different points, different concentrations of oxalate ion. That's what we're counting on. So this is 4.25 times 10 to the minus 4 molar. Okay, so here's the answer to the first question. When we start adding the oxalate, first it's zero concentration, and then it goes up slowly and slowly from 0 on up. When we reach this point at 1.15 times 10 to the minus 8, that's the lowest concentration that something happens. The calcium begins to fall out. Now the oxalate has been used up, but we can just keep adding it and the concentration will build. Eventually we hit this concentration and the cadmium begins to fall out. And then we have to go way up, go up about 10,000 times more in concentration to get the magnesium to fall out. So the calcium falls out, this is first, then second, and then third. The thing is, so we figured this out, that's nice. and we're going to need these numbers, but you can also look at the KSPs. Notice that the calcium has the lowest KSP, which means it's going to need the lowest concentration, since that's why we chose these to be 0.2. So each of these is 0.2, so we don't have anything else to worry about. They're all the same concentration, so looking at the KSPs will tell us the same thing. Whichever one has the lowest KSP, smallest KSP, should fall out first. Then cadmium, and then magnesium has the highest KSP. But that's only because we've used the same concentrations here, and they're all 1-to-1. So it can get a lot trickier if you're using different ions with different concentrations that are also if we had used silver here, then silver would be 2-to-1. But just let me assure you that since we're just starting out and you're just getting an idea of this, we're going to keep everything nice and simple and straightforward, or as simple as it gets for these types of problems. Okay, now we know this is the answer to the first question. Now they want to know when the second ion, when cadmium begins to fall out, how much calcium is left? Well, calcium begins to fall out at this point. Then cadmium begins to fall out at this point. So if we take the concentration of oxalate ion that is necessary to precipitate out cadmium and put it into the calcium expression, we will find a number that is lower than 0.2. We'll find the amount of calcium that's left over. So let's do this out. Again, it's hard to describe in words. You just have to do this out first one time to see. The concentration of oxalate ion, and at this point cadmium begins to precipitate out. So, but the calcium has been precipitating for a long time, since 1.15 times 10 to the minus 8 molar. So if we take calcium, the calcium expression, or the expression for calcium oxalate, and the KSP doesn't change, it's always 2.30 times 10 to the minus 9 for the calcium, and we put this value into the calcium expression. We found it from the cadmium expression when it begins to precipitate out, but if we put it into the calcium one, it tells us how much calcium ion is left. And that gives us 0.0307 molar. So we had 0.2. Then when we hit 0.200 molar for calcium ion at the beginning. And then we started adding the oxalate ion. The calcium started falling out. The other two ions were left alone. But then when we hit a higher concentration, cadmium began to fall out. So at that point, calcium has already lost a huge amount of its concentration, because most of it has already fallen out. Well, what percentage is left? We take that concentration divided by the original concentration times 100%, and that gives us 15.4%. That means 15.4% of the calcium is still present in the solution when the cadmium begins to fall out. Then we do it for the next one. At the concentration of oxalate ion that is 4.25 times 10 to the minus 4 molar, that's when magnesium begins to precipitate. What happened to the other ions? So what we do is we take the calcium expression. Now at 4.25 times 10 to the minus 4 molar, the calcium has been precipitating continuously since 1.15 times 10 to the minus 8. Since 10,000 times lower in concentration, it's been precipitating out like mad. So we should find that it's a very low number when we finally get to the concentration that will allow magnesium to fall out. So just put it in here. Calcium ion concentration becomes this. And so we get, what is this? So this be 5.41 times 10 to the minus 6 molar. And then if we want to know the concentration, okay, so here's our, let me do this out here, 0.23, 10 to the minus, 2, 3, divided by 4, 2, 5. 5, so, okay. Now this is the concentration of a calcium when magnesium begins to fall out. Now the percentage is what I meant to say. If you want to find the percentage, divide by the original amount. So it's 5.41 times 10 to the minus 6 divided by 0.2 times 100. And we get 0.00271%. Now, let's do it out for the cadmium. The cadmium, since it fell out second, we'd expect that it would have a higher percentage of it left over. This is, where's the cadmium? 1.50 times 10 to the minus 8. We put this same number in here. The cadmium concentration is 1.50 times 10 to the minus 8 over 4.25 times 10 to the minus 4. So 1.5 times 10 to the minus 8 divided by 4.25 times 10 to the minus 4. So this is 3.53 times 10 to the minus 5 molar. It is larger than, so 3.5 we want to figure out is percentage that's left. And we get 3.53 times 10 to the minus 5 divided by 0.2 and times 100. And we end up with a little bit about 2%, or 0.02%, or 0.0177. So you see that the calcium is nearly gone. That's almost nothing, and then this is close to nothing. So this is actually looks like a pretty good. There's a pretty good separation here for the magnesium, but for this one up here, there's 15% of the calcium left over when the cadmium begins to precipitate. That's probably not so good. So those percentages tell us what kind of separation we're going to get. When the magnesium starts to fall out, pretty much both of these guys are gone, so it's going to be a pretty pure sample. But here we'd have 15% of the calcium left over when the cadmium begins to fall out, so that's going, and the calcium is going to continue to precipitate with the cadmium. So it depends on what you're after, but usually 15% is not really good. Okay, here's another problem. I'm going to go a little faster here, but we have 0.15 molar manganese ion, 0.15 molar lead, 0.15 molar cobalt, and the KSPs for, and we're adding sodium sulfide, so you have to determine what the compound is. Now, I'll either give you the KSPs, but more likely I'll just give you the table to work with. So they'd have to be in the table. So, or whatever data that you're given. If you're given the data, the KSPs, then that tells you immediately what the compound is. But if you're just given the table, then you should be able to look at the sulfide and these ions and find those guys present. It's minus 21. Now looking at just this data, you can see this is the smallest number, so lead should fall out first, then cobalt should fall out, and then manganese. If you can't figure that out at this stage, that's okay, because we have to keep going anyway. We have no choice but to define these concentrations that will allow each of these ions to fall out of solution. So just like we did previously for manganese, the sulfide concentration is going to be the KSP over the manganese concentration. So if there's any doubt about how I got here, the KSP is going to be these two concentrations together. Now, we know what the concentration of the manganese is. It's 0.15. And notice again, they're all the same, and these are all 1-to-1 components, one manganese to one sulfide, same for these ones. They don't have to be. If this was silver, there'd be 2-to-1. It would just make it a little trickier to do. And I'm not going to put us in that situation. Let's just stick with the basics. Plenty of math here without going any further than that. For the lead, so at 1.67 times 10 to the minus 9 molar of the sulfide, the manganese begins to fall out. For the lead, it's 2.50 times 10 to the minus 27 over 0.15. This is 1.67 times 10 to the minus 26 molar. So you can see that we have to add almost no sulfide to get it to go. Just a tiny, tiny little bit. And then the cobalt, really want to skip over some of this, but I'm afraid if I do that I'll throw people off. So I'm going to keep doing this, but we're running low on time to stay under the 20-minute mark. So I'll keep going, and I might jump ahead on couple of things here, but now here's the concentrations of sulfide that will cause these ions to begin to fall out. So which one is falls out first? Like I said, it was lead. I'll just put a 1 here. For the cobalt, there's 2, and then 3. So that's the order. The lead falls out first. So the question then is, when cobalt falls out, let's say it begins to precipitate, what is the lead concentration? So that's the next question. So we take the lead, its KSP is 2.50 times 10 to the minus 27. And we see that when cobalt begins to fall out, the sulfide concentration is 2.67 times 10 to the minus 20, so we put that in here. And this is 9.36 times 10 to the minus 8 molar. So the lead was at 0.2. Now when the cobalt begins to fall out, the second one begins to fall out, we're here. It's really, really low. So let's see what that percentage is. That's what you normally want to put it in. You could stop there, but getting the percentage, oops, hopefully I haven't, yeah, so I was going to say hopefully I didn't mess up on that, making it 0.2, so that's 0.15, that's what they gave us. 9.36 times 100, so we're at 6.24 times 10 to the minus 5%. So it's almost nothing. So that's a fantastic separation. So the next thing that can be asked is when the last one starts to fall out, what is the lead and the cobalt when manganese begins to fall out? The manganese falls out at the concentration of sulfide being 1.67 times 10 to the minus 9. So the concentration of lead is going to be 2.50 times 10 to the minus 27 over 1.67 times 10 to the minus 9. So that comes up to be 1.50 times 10 to the minus 18 molar. And then 1.50 times 10 to the minus 18 molar over our starting point. So times 100%, and that comes up to be 1 times 10 to the minus 15%. That is completely cleared out. There's nothing left there. And then the what's the other one? Cobalt will be 2.67. This is also going to be very small, I can already tell. And the more of these you do, the more you'll be able to tell that too. So this is 2.67 times 10 to the minus 20 divided by 1.67 times 10 to the minus 9. This comes up to be 1.60 times 10 to the minus 11 molar. 1.60 times 10 to the minus 11 molar divided by our original value times 100%. Gives, so times 10 to the minus 8%, 1.07 times 10 to the minus 8%.